Hello everyone. Let's continue our discussion on the switching threshold derivation. So we came up with the value of switching threshold. The switching threshold is a point at which your V in is equal to V out. Okay. So this particular expression is a function of W by L of P and W by L of N. So you have value of W by L for the NMOS and for the PMOS. You take these values, you plug it over here, you get the value of R. Okay, now you take this value of R and plug it over here, you get the value of Vm. So for example, if you try to evaluate the value of the switching threshold for this transistors, you will get something like this with this set of W by L. You can just try it out. You can put these values in this expression and see what you get. Okay, so your switching threshold is equal to 1.2 volts for this set of parameters for your NMOS and PMOS. Your switching threshold is 0.98 volts for this set of parameters of PMOS and NMOS. Okay, you can just evaluate the switching threshold based on these expressions that you see over here. Okay, next step, what we are going to do is we will set the value of Vm. For example, if there is an application that needs your switching threshold to be 1.25 volts, they want your transistors to switch exactly at half of power supply. Okay, so our power supply that we assumed was 2.5 volts. We want this particular transistor to switch exactly at 1.25 volts, that is half of power supply voltage. Then to achieve that, what should be the value of W by L ratio of PMOS and W by L ratio of NMOS? So that's what we are going to derive. Okay, it's a reverse fashion. We started from this point and we calculated this one. Now we start from this point and we evaluate this one. So expressions remains the same. We just need to take this one, juggle around things a bit, and then try to get a value of W by L of PMOS and W by L of NMOS as a function of Vm. In this case, Vm is a function of W by L. We have to do a reverse way around. We have to take W by L and make it a function of Vm. So let's see how do we do it. It's a pretty simple derivation we have. Okay, so I have just mentioned over here, alternatively, the required ratio of PMOS and NMOS transistor size can be derived such that the Vm is set. Okay, I'll tell you one application where, for example, you have a clock inverter. Clock inverter has got the PMOS and NMOS sizes should be exactly the same. If they want the sizes to be exactly the same, then only there is a possibility that your switching threshold will be coming exactly at the center. And for that, what should be the value of W by L ratio of PMOS and W by L ratio of NMOS? So that kind of applications needs special way you design your CMOS inverter. Okay, so I'll come to that application, the application that I just talked about. I'll talk about that application in my following slides. Let's move on with the derivation, the analytical part first, which is the tedious one. So you have your expression, which is IDSP is equal to negative of IDSN. We just reversed it over here. We have told that IDSN is equal to negative of IDSP. Okay, so all the n's, the suffix n's represents, this is all are related to NMOS transistors, and the suffix xp denotes that these are all related to your PMOS transistor. This is what we had done some time back. So your IDSN is your negative IDSP. So this negative sign will take it inside the brackets and see what happens. It basically all the negatives one will become positive and the positive VM will become negative. So it's a pretty simple one. The negative VM plus VDD plus VT into VD sat P plus VD sat P square is equal to Kn and this whole bunch of equations over here. So this is now equal to this, and it's when we try to solve this, we get the value of Kn and Kp. Since Kn and Kp are a function of W by L of PMOS and NMOS, we'll take this Kn and Kp to the left hand side and keep all the expressions on the right hand side and see what do we get over there. Okay, so your Kn, from the previous equation, you see that this VD sat N is common in this expression and VD sat P is common in this expression. You just take this outside expression and see what you get. So you have Kn VD sat N and this bunch of things, and you have Kp VD sat P and this set of expressions. Okay, we'll try to just juggle around these things as well. You have Kp VD sat P divided by Kn VD sat N equal to what you see at the right hand side. It's just a simple matter of playing with the division equations. You have Kn VD sat N, we have taken this one at the bottom and did the equation formation. So you have the Kp VD sat P divided by Kn VD sat N equal to what you see at the right hand side. The equation is a bit complex, but it's fine. We can still manage. We can still do some hand calculations based on these equations. If you want to go for more accurate models, the equations becomes a bit complex and these are all automated. So these are only for hand calculations. Okay. just to understand things, where are we doing things correctly. Okay, so we just expand your kp to kp dash w by l of pmos and kn dash w by l of nmos. So we know this, the gain factor, the kp and kn are the gain factor. That's basically a function of your process trans conductance and the w by l ratio of pmos and nmos. So we know that. We just expanded it, and there you actually go. You see, if you see towards the left hand side, you have an expression where you have w by l of pmos, you have an expression where you have w by l of nmos, and all this can go to the right hand side, and you get a left hand side w by l ratio, which is purely a function of vm, which is purely a function of switching threshold. You just plug your switching threshold values over here, you just plug what you have over here, and you will get a value of w by l of pmos and w by l of nmos. So let's do that. We'll do that. So we have w by l of pmos and w by l of nmos, and the right hand side you have everything. You have all of them are constants except your vm. So you plug your value of vm, and you will get, you basically plug a value of vm over here, and the rest all are constants which you will get from a model file, and you will get a w by l ratio of pmos equal to x or y w by l ratio of nmos. So for example, in this case, if you see, the w by l ratio of pmos is 2.5 times w by l ratio of nmos. Okay, if you try to use a calculator and identify the if you try to divide 3.75 by 1.5, you will get the value as 2.5. So this is what you will get. You will get an expression which says that your pmos should be n times greater than nmos, and you can decide the value of n based on the size of your transistor. So let's do that. Let's see. So for example, this brings us to a very important concept where this particular expression you can use this particular expression to get the value of switching threshold on an existing or predefined w by l ratio of pmos and nmos, and this expression will take you to the value of pmos and nmos, or basically how much bigger your pmos should be greater than nmos based on what value of vm you want it to be. So this brings us to a very good example. What we'll do is, from the next video, we'll do some spice simulations, and the spice simulations will be based on certain table. Okay, we will have a w by l of the pmos, we'll have x w by l of the nmos, and x we are going to vary the value of x, and then trying to do the spice simulation and see where does the switching threshold lies. Okay, so it will be something like this. You will have your w by l ratio of pmos, which we have kept constant, and we will try to keep the w by l ratio of nmos also constant, and based on the value of the integer that you see over here, the w by l ratio of pmos will be increased. So in this case, your w by l ratio of pmos is equal to w by l ratio of your nmos. Sorry, w by l ratio of your nmos is equal to w by l ratio of pmos. So this is this particular example which we have already done, and for this we got a switching threshold of about 0.98 volts. In the next example, it says that w by l ratio of pmos is twice the w by l ratio of nmos. So in that case, your w by l ratio will be, your w will be 0.375, l will be 0.25 for your nmos, but for your pmos will increase the width twice. Will make 0.37, will make the width of the pmos as 0.375 into 2, and the channel length will be same. We won't modify the channel length. In that case, you will find that your pmos size will be twice than your nmos size, and see what you get the value of switching threshold. We'll do the same for all of them, and parallelly, while shifting the switching threshold, while calculating the switching threshold of this transistor, we are also going to evaluate a rise and the fall delay for similar kind of inverters, and see what do we get. So when you try to calculate the delays of cell, that becomes a dynamic behavior of your CMOS inverter, which we are going to just touch upon in this particular set of videos. Okay, dynamic behavior will be covering in a separate course. This course focuses mainly on the static behavior, but we will touch upon the dynamic behavior of your PMOS and NMOS and a CMOS inverter as well, using this particular table. Okay, so let's try to come up with some more spice simulations, a more transient analysis of the CMOS inverter. Let's try to do all this in the next video. Thank you.